In Module 4, we're going to take up the topic of equilibrium in chemistry, and I want to start that by introducing you to a concept of dynamic equilibrium, which you may or may not be familiar with. Our learning goals in this video are going to be to recognize the difference and basically contrast static versus dynamic equilibrium, and then I want to talk about some of the features that describe a dynamic equilibrium at a microscopic level. Now, equilibrium, you may already know what equilibrium is, but we're going to describe it as a state in which all the forces are balanced. And because they're balanced, there's nothing that is inducing change in that system. A static equilibrium is basically something that you find in a mechanical system. So I want to talk about that a little bit, but most of the time we're going to be talking about a different kind of equilibrium, but I want to be able to contrast these. All right, a mechanical system is one that's usually influenced by forces of different kinds. So the easiest force for us to relate to is gravity. So imagine that this is a hill, a terrain over which you can travel. So you've got a little bit of a hill and a little bit of a valley and some flat territory out to the right. Now, a static equilibrium means that we're going to be in a place where there's no forces that move us one way or the other. And typically in physics, what this means is that we're going to have a flat territory, basically where the slope is zero on this surface that describes a force. So when we talk about where equilibrium positions are likely to be found, we need to look for the places on this surface where the slope is going to be flat. So I want to describe three different types of equilibrium in this case. The first one is a neutral equilibrium, which we might find on that flat area on the right side of the curve. It basically is an equilibrium at which if we were to nudge a ball that's lying in a neutral equilibrium spot, it would move and it would stay permanently fixed in a different place. So it wouldn't be absolutely motionless, but it would not return to the place where it was. A second kind of equilibrium is a stable equilibrium, and that's the one you might find at the bottom of a valley. In this case, if we were to nudge that ball, it would oscillate back and forth through that valley, so it wouldn't ever stray very far from its stable equilibrium point, and if there's friction involved, it might ultimately respond, it might actually return to that stable equilibrium point. Finally, an unstable equilibrium would be the one at the top of the hill, where the slope is zero, and we could, with great care, set a ball there so that it wouldn't move, but any slight nudge on that ball is going to cause it to actually move quite far away from that equilibrium point. And so that's the essence of an unstable equilibrium. Now, I want to point out that there are other kinds of stability, and I might cite for one example, the amount of water in a lake is often a stable entity. But you want to think about, is this a static equilibrium or not? The amount of water in a lake isn't really a mechanical system, and in fact it is more emblematic of a different kind of equilibrium, one that we're going to talk about now, dynamic equilibrium. So dynamic equilibrium is essentially a stable state that exists in a time-evolving system. The system itself must have several features. First of all, it has to have smaller mobile units. These are the things that are continuing to move even while the system itself is at a state of equilibrium. It needs to be a closed system. That is to say, it's not exchanging matter, not exchanging material with any other part of the universe. And it needs to have reversible dynamics. Typically, we're going to be looking at systems where there are one of two or more possible states that the matter can be in, and it's constantly exchanging itself between these different states. Now, the key with dynamic equilibrium is that on a large scale, it appears to be quite stationary. You can't tell if you're far enough away, you can't tell that anything is changing in it. But if you were to zoom in and look at it on a very small scale, you would see continuous movement. A good analogy for this might be the crowd in a stadium. Now we're looking at it down from an aerial view of a stadium which is holding some kind of athletic event, and from this aerial view it just looks like a full stadium. You can't really tell that there are people moving around in that crowd. They're just filling the stadium. But if you were down in that crowd itself, you would see that people were constantly getting up to go get refreshments or go into the restroom or going to visit with friends in another section. They would be moving continuously, and you would be aware of that if you were there, but if you're looking at it from down on high, you wouldn't be able to see all that movement. So this may be an example of a dynamic equilibrium involving people in a stadium. Now, another good example of dynamic equilibrium is something I'll call thermal equilibrium. I want you to imagine two objects that start at different temperatures, and they're going to be brought into contact with one another. So on the far left side of this picture, you can see the two objects. One is at a high temperature marked H, one is at a low temperature marked L, but they're not in contact with one another, so they're keeping their temperature. When they're brought into contact, what we begin to see is some movement of the heat from the hot side to the cold side. And in fact, that's one of the laws of thermodynamics, is that it's always going to move from the hot side to the cold side. After some period of time, we'd end up on the right-hand side where both sides, both objects, are going to be at the same temperature, and therefore they will be in thermal equilibrium. So this is going to be our functional definition of thermal equilibrium, that both objects have the same temperature. Now, I want to point out that temperature is associated with motion, and this continues even when it's at equilibrium. So this is the sense in which this system is a dynamic equilibrium, because the particles that are in these two objects are continuing to move. They're continuing to bump into each other on the boundary between where they're making contact. So there's still some kind of energy exchange going on. It's just not going to be a meaningful one in the sense that these two objects will remain at the same temperature. Now, I want to extend this a little bit to talk about phase equilibrium and what that looks like on heating curves. And I want to say a few words about phase equilibrium. First of all, again, because temperature induces motion, as temperature increases, we have molecules that move faster. So what this means is that even though molecules tend to stick together, as they're moving faster, they're less able to stick together. And this is what ultimately causes a more condensed physical state to transition into a less dense physical state. So for example, a solid goes to a liquid, or a liquid goes to a gas. And this all happens as we increase temperature because we're increasing the speed at which particles move. Now, we saw in the previous module an example of a heating curve. Let's ask what happens at a phase transition. So I'm going to show you a heating curve again. We were focused on the central part of this curve in the last time because the slope was related to the heat capacity. But now I want to focus on a different part of this heating curve. Again, we're talking about heating up water and measuring the temperature change that accompanies that. But I want to look at this flat area because it turns out to be the place where vaporization is occurring. It's right at the boundary between liquid water and steam, as shown in the lower diagram. It represents a flat region in the temperature at 373 Kelvin, which is the boiling point of water. So what's happening here is that we have, in essence, a phase equilibrium that's going on at that big flat area. And that phase equilibrium is a place where the water in the liquid phase is exiting to go to the gas phase, but we also have gas phase molecules that are re-entering the liquid phase and becoming liquid. So it's a true equilibrium in the sense that there are particles going back and forth between liquid phase and gas phase, and it's all happening right on that level part of the curve. We'll learn more about this dynamic equilibrium as we look at some more systems in the next few videos.